So in this video we're going to look at conditional probability, which is when we have two events which are not independent from one another, they're non-independent events. Now what do we mean by this? Well, in the last video I gave the example of a deck of cards, so let's choose that one again. Let's just write then, well, what would be the probability if what sort of thing might we want to calculate? Let's say the probability of drawing a king this time. I think we had an ace last time. Probability of drawing a king then. So in the first round, if you like, when we first draw a card, event A, we say it's the probability of, well, just drawing a king is going to be 4 out of 52. Okay? Now, if it was a dice roll, the probability of drawing another king would simply be the probability of event B, which would be, completely independent of this. If it was a dice roll, in other words, it would be 1 in 6, and here it would be 1 in 6 again. But with the deck of cards, where we're not replacing the card, so without replacement, then the probability of B, depends on the probability of A. So we say, instead of probability of B, probability of B conditional on or given that something happened in A. So probability of B given A. So that's the essential difference. If we follow these lines down here, this would be a king, this would be not getting a king, okay? So this is not getting a king, so we've got the probability of non-B, or not B if you like, again, conditional on whatever happened in A. So that's that line here of our tree diagram. That's these two pathways here. Now, we've also got to fill in the bottom half of our tree diagram to be complete here. So we've now got the probability of all other options. In other words, not getting a king. So we say not A. In other words, we've got 52 minus 4, which is 48 over 52, when we first draw our card. That's the probability of not getting a king. If we look in the second draw then, where we haven't replaced the card, what have we got? We've got the probability of B, but not just the probability of B, the probability of B given that we didn't get a king in the first round, like that. And here, this is a king and a not king outcome. So here we have the probability of not getting a king in the second draw, so we say not B, given that we also didn't get a king in the first draw, so not A, like that. And we can fill in these probabilities now. What is the probability of B conditional on A? Well, conditional on A, we drew one king here, so the first thing is we've only got 51 cards left. Okay? The second thing is, if we already drew a king, we've only now got 3 that we can draw, so it must be 3 out of 51. Let's look at this branch then, the probability of not drawing a king, given that we did draw a king in the first draw. Okay? Well, if we did draw a king, again, we have a reduced probability. The easiest way of calculating this is realizing that these probabilities must add up to 1. So again, it's going to be out of 51. We've got 51 cards now. And if we think of 51 cards, subtract 3, then we must have 48 left. So we've got 48 out of 51 probability of not getting a king, given that we did get a king in the first draw. Okay? Now if we follow along this pathway, we didn't get a king in the first draw here. Sorry, let's put our equal sign there. So we say, what's the probability of B given that we didn't get a king in our first draw? Well, if we didn't get a king, there must be 4 left. So logical reasoning tells us that we still have 4 kings that we could pick. And possible outcomes are again 51 because we did draw some card. And here, again, if we realise that these branches must add up to 1, it's a nice straightforward calculation to say, well, we've only got 51 cards. If we subtract 4 from 51, we get 47 out of 51 as our probability. So this is an example of conditional probability. Let's look at a couple more. Okay, in this example then we've got 5 netball players, and what we're going to do is select first of all a captain, and that would be our first event, but the event we're really interested in, that we're going to calculate the probability for, is the second event where we pick a reserve captain. So it will be either Jackie, Rosie, Mary, Brenda or Jane, and the question we're going to ask is what's the probability that we're going to pick somebody whose name begins with J in the second round. Okay, let's just write it like that. So what's the probability we're going to pick somebody whose name begins with J in our second selection when we pick our reserve captain? Okay, and that's when we've already picked our captain, so there's going to be obviously one less person to select from because we can't have a captain and a reserve captain. So it's our probability for somebody whose name begins with J in the second round obviously depends on what happens in the first round. So this is conditional probability. Good, let's work it out. So we've got, well, we start here, we use our probability tree diagram, and we're trying to find out if we've got a J or not a J in the first round before we move to the second round, the second event, where again we're trying to see whether we've got a J or a not J, a J or a not J. So the first probability, probability A, is going to be when we pick J in the first round, or somebody with J in the first round. So that could happen here or here. So we've got a 2 out of 5 chance. So the probability of A is 2 over 5, 2/5. We can fill in this branch as well because we're going to need this one. So probability of not picking J, somebody whose name begins with J in the first round, is going to be the complement of 2/5. In other words, 1 minus 2/5, or 3 out of 5, 3/5. Okay, so that gets the first event done. But what we're interested in is the second event, which depends on the first event. So now we move to the right-hand side of this tree diagram here. Well, the probability of the second event, which we'll call B, depends on A. And what's it got to be? Well, let's use logical reasoning to work it out. We've already picked somebody, so there's only 4 left to pick from, so it must be out of 4. And if we've already picked a J, then we've either picked Jackie or Jane, so there must be only 1 J left, so it's got to be 1 out of 4. Now, we don't need to do this branch. We could very easily do the probability of of not B given A, but we don't need to. It would be 3 out of 4 though, because obviously it's a certainty that we're going to pick somebody, so it's going to be the complement of 1/4, which is going to be 3/4. But I'm going to leave it blank because the one that we're interested in is this outcome here. Okay, let's do the other possibility. The only other possibility is we go down this route where we don't pick a J in the first round, which is 3/5. So the second round, again, the probability of, well, this time we've got B given not A here, and that must be out of 4 again. But this time, well, we didn't pick a J, so we've still got 2 J's available, so it must be 2 out of 4. And here, again, we don't need to do this, but the probability of not B given not A would be the complement, which would be also 2/4. This is the one that we're interested in though, or this one here. Okay, so it's this or this one. Either of those two possibilities. So if it's an or, we're going to add them together. So in other words, what we've got is 2/5 and 1/4 when we go down this route here. So 2/5 and gives us, we multiply when we've got an and. So that's our first route through this diagram, and our second route going down here is going to give us, well, or, so we're going to add 3/5, again times, because we've got to have both of these conditions, so both and means we multiply, so 3/5 times 2/4, and that will give us our answer for this question. Okay, all we've got to do is work it out. So we've got 2 times 1 is 2, and 5 times 4 is 20. And now add 3 times 2 gives us 6, and 5 times 4 gives us 20 again. So our answer should be 8/20, or if I divide top and bottom by 4, I'll get 2/5. So there's our answer, 2/5, or I suppose you could say 40% chance of picking somebody whose name begins with J in the second selection for reserve captain. So that's answered the question. But how confident are we that we've got the right answer? Well, there is a way of checking, and that's to work out all the possibilities. In other words, to list out our sample space. Now, with conditional probability, a grid diagram isn't going to work very well at all. It's going to be difficult to fill in. So a tree diagram works perfectly well. If I start here, that should be okay. So let's look at our 5 options in the first round. So if we go 1, 2, 3, 4, 5, like that. That will give us, well, let's put our J here. We've got another J there, and we've got a B here, an M here, and an R here. So that's the first round done. So we've got 2 possibilities for J out of 5. Now, we've said that in the second round we've only got 4 people left, so we just have 4 branches coming off each of these. So 1, 2, 3, 4, like that, and 4 off these. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that's our 2 events, and on the outside we'll get our sample space. So if we had a J here, then we might have another J here, but we also might have M, R, or B. If we got a J here, again, we might get another J, or M, R, or B. Here, if we got a B, well, we've got 2 J's available, but we don't have B available, so we've got M and R. Here we've got, again, 2 J's available, but we don't have M, so we must have R and B. And here we've got 2 J's, and not R, but M and B. So, takes a few seconds to draw that out, but now what we've got is a full sample space. Now what I'm going to do is I'm going to highlight, let's use a different colour here, let's use that. Okay, I'm going to highlight all the outcomes that are favourable. In other words, we've got a probability of J in the second round as our question. So when do we get a J in the second round? Well, we get one here, we get one here, 2 here, 2 here, okay, and 1 there, and another one there. So that's the total number of possible outcomes. Let's just do a little bit of calculation on this. So we've got how many? 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 possibilities. And what's the total number of possibilities? Well, for each one of these branches we've got 4, so it's 4 times 5. Let's just write it down like that. 4 times 5 possibilities around the outside gives us 8 out of 20, which indeed is 2/5. So this is our check, and it confirms our answer that we got using the simpler tree method, and so we say 2/5 or 40% must be correct. And lastly, if we look at one more example, let's have a look at the classic example of a sock drawer. Okay, picking socks from a sock drawer, and let's just define how many socks we've got in our sock drawer. So if we've got the options are purple, red and orange, let's have 3 purple socks. Okay, 3 red socks, and let's have 3 orange socks as well. Keep it nice and sort of symmetrical. Okay, so we've got 9 socks in our sock drawer, and we're going to try and work out the probability of this time a matching pair of socks. So a matching pair of socks. In other words, we've got several combinations here. We've got a purple, we could have purple and purple, we could have red and red, or we could have orange and orange. And so we could work this out in 3 operations. So we could say purple or not purple, and do that 3 times, and then add those together. Now that's going to be a long-winded way of doing it. So what I'm going to do instead, let me just erase those, is show you a slightly quicker way when you've got sort of 3-way choices like this. Okay, let's now draw a 3rd branch here, and then branch that into 3, and these into 3, and these into 3. Okay, so we've sort of trebled our branches. Instead of bifurcating them, instead of splitting them into 2, they're split now into 3. So our first event, I've drawn it a little bit wobbly here, but our first event is to the left of this dotted line here. Okay, so if I draw that down through there, then these 3 branches here excuse me, will be our first event. So if we now fill in our probabilities, let's have a look at those. So we start here, and we say, well, this is our purple branch, and instead of having not purple, we're now going to have just red, and then we're going to have orange. Okay, so now the probability of picking a purple sock in the first round, then in the first draw, if you like, is going to be, in fact, I won't use the word draw because that will be confused with the physical thing, the draw. So we'll just say the first round. Okay, the first event. So the first event is that we do select a purple sock, and so there are 3 of them. So it's going to be 3 out of the 9 total. Okay, because we've got 9 socks altogether. The red must be the same, and so must be the orange. So that's completed the first event. Okay, so now if we dip our hand into the sock drawer again and randomly draw a sock, we're going to again either get a purple, a red or an orange. And this will always be the case because there's so many of these socks that we haven't eliminated all of the purples, all of the reds or all of the orange. Okay, so we've got PRO option in the second event. Okay, so now if we pick a purple but we've already picked a purple, then it must be a 2. We must have 2 chances out of, well, we've already picked one, so it's 9 minus 1, 8. So it's 2 out of 8. To pick a red, we've already got reds, so 3 out of 8, and 3 out of 8 for orange as well. Along this line, we've got red. Well, here's our 2 out of 8 option, so the others must be 3 out of 8, and 3 out of 8. And here we've got orange, so here's our 2 out of 8 option, and 3 out of 8, and 3 out of 8. So that's completed our probability tree. Now we've got to do is find out all the ways of getting a matching pair. Well, purple and purple is going to be a matching pair, so there's one there. We've got a red and a red, so there's one there. And we've got an orange and an orange, so we have one there. And again, we've got this or this one or this one. Okay, and when we've got either this or, whenever we've got or, then we're adding. Okay, so it's an addition operation, just as in number arithmetic. Okay, so let's multiply, first of all, these two together, because this is a both and, so here's where we get our and. So we now need to simply multiply these together and then add all the probabilities. So we've got probability of a purple sock is going to be 3/9 times 2/8. Probability of a red sock is 3/9 times, well, it's going to be 2/8 again, isn't it? And in fact the orange sock is going to follow the same pattern. So what I'm going to do instead, I think, is if I erase this, because I realise I've got a pattern now, 3/9, it's easier to say 3 times, okay, like that, 3/9 times, what did we say, 2/8, okay? And then we can simplify this, because then we've got 3 times, well, 3/9 is 1/3, and 2/8 is a quarter. So it's going to be 3 out of 12, which is getting a little bit cramped here, but I think you can see it clearly. 3/12 is going to be 1/4, or 1/4, or 25% if you want to convert it to percentages. 0.25. Okay, so that's worked out our probability of selecting a matching pair. But is our answer correct? Well, let's check by looking at the sample space. So if I think about the sample space, I have 9 socks in my sock drawer, so if I'm going to draw this, I'm not going to be able to do it using a grid, so I'm going to, let's do it like this. I'm going to draw 3 arms like that, and then I want 6 more, so I'll have 2 in there, 2 in there, and 2 in there, like that. Okay, so that's my first round. Now that's 9 possibilities, and each one of these arms, so I'm going to have to draw this a little bit more cleverly like that. Each one of these are going to have 8 options coming out of those. So how am I going to do that? Let's see. Let's go like that. 1, 2, 3, 4. Okay, if I bifurcate to start with, like this, then I should be able to just about squeeze in my other options in between these forks. Okay, like that. Right, it's going to be tricky, but I think you'll get the idea. In fact, what I'll do is I think what I'll do is just go, so I need 6 in each one, don't I? 1, 2, 3, so 1, 2, 3, 4, 5, 6. Is that 6? Yeah, join those up. So it's going to look like that. It's going to be very, very cramped, but it should be just enough space to show you what's going on. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, this one's tricky. Let's do a couple there. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, nearly there. 5, and then 1 there. 1, 2, 3, 4, 5, 6. There we go. 1, 2, 3, 4, 5. Let's have one here. 6. Okay, so you can see now with this diagram that what I've got is, okay, radiating from the center, 9 arms. Radiating from each of these arms, I've got 8 arms. So I'll end up with total, let's call it the sample space size of 8 times 9 equals 72 possibilities. Okay, so there we are. Didn't take too long. It's a complicated diagram, but it's useful if I want to do a check. So I'm going to show you how I can quickly check using this method. So I've got, well, what have I got? I've got purple, red, or orange there. Let's have another purple, red, orange here. Purple, red, orange, and purple, red, orange going here. So on the outside, well, if I got a purple, I must have a purple and another purple option, but the others are going to be red, 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 and orange, orange, orange. So it's going to be like that. And when I've got another purple, so down here, it's going to be the same pattern. So it's going to be purple, purple, red, 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 orange, orange, orange. And I should have another purple here. Where's it gone? P-R-O, P-R-O, P. That should be a P there. Okay. So P, P, R-R-R, O-O-O, like that. We've got an orange here, so we must have 2 oranges here, and then P, 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 and then R, R, R. What have we got here? Another orange, so orange, orange, P, 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 R, R, R. Let's go down this line now. Orange, orange, P, 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 R, R, R. So we're getting there. Okay, we've got a red here, we've got an R, R, then, but we then have a P, 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 O, O, O. Here we've got a red, so we've got R, R, P, 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 O, 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 and a red. So R, R, P, 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 O, O, O. Phew! There we are. Those are all 72 of our possibilities, our sample space. Now I'm going to switch to a highlighter pen. Okay. Because what I want to do is highlight all the possibilities where I've got a pair. So here I've got P and a P twice. So 1. Actually, this isn't going to work, is it? I'm going to have to highlight, so I'm going to have to ring rather. So I'm going to go back to my felt tip pen and use a red instead. So I've got a P there and ring another one there. So that's going to happen here, here, and where's the other P? Here and here. So there's 6 of those. Let's choose a different colour pen. Let's look at the reds now. So we've got a red and a red twice here. We've got a red and a red twice here. And we've got a red and a red twice here. So 6 again. And it's going to be the same with orange, but let's just work it out. Okay, whoops. There we go. Right. So orange, we've got 2 there. We're going to go down this orange pathway here. We've got 2 here. And this orange pathway here. We've got 2 here. So good, that completes our analysis. Now, all we've got to do is total them up. So what have we got? We've got, with these red ones here, we've got 6 out of our 72 possibilities. Or we might have gone down one of these green routes, so or means add, and again we've got 6 out of 72, okay, or 6 out of 72, so I suppose I could have done 3 times 6 out of 72. Well, what's 6 out of 72? Does 72 divide by 6? Well, 72 divides by 3, so we could think of it that way. giving us 24, so it's going to be 1/12. Let's just check. 6 times 12. Okay, 6 2s are 12, 6 1s are 6, add 1 gives us 72. So just going over to one side there just to confirm our arithmetic. So that means we've got a 12th plus a 12th. Whoops, I wrote the wrong symbol there. That should have been plus a 12th, or I could have said 3 times a 12th. Let's just get that right. 3 times a 12th, in other words 3/12, which again equals 1/4. So it's a way of double checking, doing the same sort of arithmetic but in two slightly different ways to make sure that we've got the right result. And we have got the same result, so I'm going to say this answer must be correct. Okay, now it started raining, so apologies if you can hear the sound of the rain, but it's rather nice summer rain. Okay, now lastly we're going to have a look at the the difference between independent probability and non-independent probability. So let's have a look at this run of luck on 6 dice. Okay, we've managed to roll 6 4 times. Let's have a look at the probability tree that extends from that then. So we must have gone down this route, so we had a 1 in 6 chance of getting this first 6 and 5 out of 6, but we beat the odds. We got a 1 in 6, so we got a 6 here. Okay, so we say probability of getting, let's put 6, S for 6. Okay, successful outcome. Now in the second event, what happened? Well, we had another 1 in 6 possibility, so nothing changed at all. So there was no memory of what happened here. There was still a 1 in 6 possibility and a 5 in 6 chance that we weren't going to get a 6. Again, here 1 in 6 to get an S, no change at all. So that's 1, 2, 3, and then our fourth occasion we just happened to roll a 6 again. So what's going to happen on the 5th roll? Well, a lot of people say, and this is called the gambler's fallacy, a lot of people say, well, the probability must change in some way. And there's two ways it can go. Some people say if we roll a 6 again, well, that's going to be really, really unlikely. Okay, because they reason it's already happens 4 times. It's so improbable that it will happen again that there must be some kind of memory that the dice has of all these events that went before, and so it can't surely come up 6 again. Well, yes, it can, because it's still a 1 in 6 possibility. Or people say, well, it's likely. You know, have a look at the evidence. We rolled a 6 4 times. Looks like there's some kind of likelihood that it will come up again. So if we roll a 6 4 times, it's very likely that it will come up again. So there's a greater than 1 in 6 chance that we'll get a 6 on the 5th roll. Well, all of these are committing the gambler's fallacy, which can be summarized as saying that if you think in that way, you don't realize that these are independent events. So it's independent probability that you should use to calculate the answer. And if you wanted to find out what would happen on a 6th roll, you could go on forever. One of the characteristics of independent probability is it's sort of infinitely extensible. It can go on forever. We can keep branching this diagram and we'll still get the same thing. Okay, what's the difference then? Well, typically with non-independent events, so let's have a look at a non-independent event. Something like this. So we've got a biscuit jar and we've got 5 cookies in here and we want to select a strawberry cookie, let's say. Okay, we want to select a strawberry flavour. So with situations like this, typically we're taking away from a collection, in this case of biscuits, or a population, say a small group of people, or a large group of people. So a collection or a population that goes down, diminishes, will typically give you conditional probability, because these are non-independent events. And again, we can see this on a probability tree diagram. So if we have a look at this, now I'm covering it up with a label because obviously it has to be a random selection, otherwise our numbers would be very different. So it's a random fair selection. So we've just said 5 cookies, 2 strawberry, 3 chocolate, but we're not going to obviously look before we dip our hand in. Okay, so let's draw our probability tree. Okay, so we start here. We want a strawberry, so let's call that S again. And we're going to say, well, how many cookies are there? So there are 5, so there's 5 possibilities. So we've got a 2 in 5 probability that we're going to pick S, a strawberry flavour. Again, if we go up here, we're going to get, well, no, not a 2 in 5. In fact, a 1 in 4. Because it's conditional on what happened here. Okay, conditional on the first round, drawing an S. And that changes all the numbers. So the probability goes down. Well, the probability doesn't necessarily go down, but it changes. So our numerator goes down. We have a 1 instead of 2 because we've already selected strawberry. And we have a 4 instead of a 5 because we've only got 4 cookies left. Now what's going to happen on the next branch of a probability tree? See if you can think through what the probability would be next time round. Well, next time round it's got to be out of 3. Okay, but we're going to have a 0 chance of drawing a strawberry flavoured cookie on this branch of the tree because we've already drawn our 2 strawberries before. So again, this is very characteristic of conditional probability, that we kind of run out of options and we're getting a 0 here. 0 out of 3, of 0 divided by 3 is of course just 0. So a 0 probability there, and again, that was a strawberry there, so again, if we draw again, we're going to have a 0 out of 2 this time. And finally, a 0 out of, well, we've only got 1 cookie left. And so what also happens with this kind of probability, when we're selecting from a bag, say, or a population of people, or from, in this case, a biscuit jar, is we run out of things to select. If we think about a pack of cards, eventually we're not going to have any more cards. If we think about a raffle, eventually we're going to use up all of the raffle tickets. So you could say one really notable difference between independent and non-independent events like this is that typically you run out of possibilities, and so it's a finite probability tree diagram. Okay, well, I hope that's helpful. You might want to think of other situations after you've looked at this video. You might want to work out for yourself what the difference is between independent and non-independent events. And a good way of doing that, again, is to draw out the probability tree and see what the characteristics are of an independent situation, independent probability, and non-independent probability, where you've got conditional probabilities which tend to be finite.